So today we have a lot of material to cover. We're going to start with looking at graphs of functions, a couple of vocab words, so if you want to pull up your vocab sheet. We've got turning points. This is where a function changes from increasing to decreasing, or where the graph turns. It's kind of self-explanatory. But the multiplicity is important because if a function has a repeated zero, so for our example here, we're looking at this binomial right here, where the power is 2. That means the zero is repeated. You could write it out as x minus 3 times x minus 3. What that means, if the zero is an even power, it's repeated an even number of times. If it were an odd power, this wouldn't be true. But the zero will be a turning point of the graph. So that'll be helpful when we go to put all this information together. The first graph we're going to start with is 5x squared minus x cubed. Step 1 for graphing is the leading coefficient test, or determining the end behavior. You should know kind of what your graph will look like before you put it on the graph, so that if you made a mistake somewhere when you go to graph it, you can know if it looks right or if you need to go back and check your work somewhere. So step 1, instead of writing out the as x approaches negative infinity, that's not going to be as helpful for graphing purposes as just sketching what the graph should look like. So the leading coefficient test, our highest power, this is not written in standard form, so we have to look at this term right here. Our highest power is 3, so we know it's going to look like a snake. And the coefficient of that term is negative, so we know instead of rising to the right, it is going to fall to the right. Step 2 is finding the zeros. So we're going to factor our function. Actually, we're going to substitute 0 for f of x, and then I'm going to factor out the x squared. So that'll leave us with 5 minus x. Now notice this term right here has an even power, so that means this 0 is repeated, which means it will be a turning point of the graph. So to find the zeros, I'm going to set each piece equal to 0. This is our zero product property, and solve for x. This one, taking the square root of both sides, we get x equals 0, but I'm going to mark that it is a turning point so that when I go to graph it, I remember that. Here, adding x to both sides, we get our other 0. It's helpful if you write your zeros as ordered pairs. Again, less to think about when you go to graph. Make sure you get that x coordinate first, and we substituted 0 for y second. Last is we need to determine what other turning points are on this graph. So if you think about the fact that our graph is going to go through this point right here, and I'm going to count each of these by, this is 1, 2, 3, 4, 5, and it's going to go through the x-axis right here. So somewhere in between these 2 points, it has to turn so that it comes back to the x-axis. All right, so we're going to set up a t-chart just between our x-intercepts. So we only need to test the values 1, 2, 3, and 4. So we're going to substitute these values back into our function. So substituting 1 into the function, I'm not going to actually show the substitution. I don't want to take too much time in the video. We would get 4 for y. Substituting 2, we get 12. Now you notice the graph is still going up. It hasn't turned to come back down towards the x-axis again, so we have to substitute 3. We get 18. Graph is still increasing. When we substitute 4, we get 16. So we notice now these y values from 18 to 16 start to decrease. 18 is our highest y value, so here's going to be another turning point of our graph. And because I scaled these by 1, this only goes up to 10, so I am going to rescale these. Right here will be my x-intercept of 5. So you can plot all of these points, or you can just plot your turning point and give me a quick sketch of the graph. So that's what I'm going to do. I'm going to plot 3, 18. And using the sketch that I put in part 1 with the leading coefficient, I'm going to start up, come down to this turning point. I identified this 0 as a turning point. So I'm going to come down to that turning point, up, and back down, and I'm going to try and sketch this carefully. Messily is how I'm going to sketch it. So hopefully you have an idea of what this graph is looking like. Let's look at another graph. This time our equation's a little bit more complicated. So the process is the same. Make sure you understand that leading coefficient test and how to identify what your graph should look like. This time it is in standard form, so we have the highest power of 4, and the leading coefficient is positive. So it's going to look maybe like a W opening up. To find the zeros of this one, whenever you see a quadnomial, meaning 4 terms, you should think factoring by grouping. So when I set this equal to 0, I'm going to start to factor by grouping these two terms, have a common factor of x cubed, leaving me with a 3x minus 4. And then these two terms, the only common factor is 1. If you're one of those who likes to see the 1, go ahead and write it. I don't usually write my 1 there. And then the 3x minus 4 becomes our GCF, so we're going to factor that out. And we're left with x cubed from our first term and plus 1 from our second term. Now, most of you would probably stop here. I hope some of you recognize that this binomial right here is a sum of cubes. We can continue factoring that. So I'll give you a reminder of factoring a sum or difference of cubes. You take the cube root of the first term, keep the same sign, cube root of the second term. And now for the second part, we're going to be using the x and the 1. We're no longer using the x cubed and the 1. So we take the first term and square it. Opposite sign, take the first term times the second term, always plus second term squared. Setting each piece equal to 0, our first one we have 3x minus 4 equals 0. Our second term we have x plus 1 equals 0. And our last term we have this whole trinomial equal to 0. By the way, when you use the sum or difference of cubes formula, that trinomial will never factor. There's nothing that multiplies to positive 1 and adds to negative 1. So when we solve that one, we're going to have to use the quadratic formula. Our first term adding 4 and dividing by 3. Our second term subtracting 1 from both sides. And for this one to test if the zeros are even real, I'm just going to check for the piece under the radical first. So under the radical is b squared. And I always drop the negative if b is negative. Once you square it, it becomes positive. And then there's less mistakes that you can make if that negative is out of the way. Minus 4 times a times c. So what I'm getting is 1 minus 4, which is negative. So these roots will be imaginary, so I don't have to worry about actually finding them. So I've only got 2 roots that I'm actually going to plot on my graph. And now I need to find any additional turning points in between them. So I'm going to set up my t-chart. And we've got between -1 and 1 1/3. So I really only have to check 0 and 1. Those are the only integers between my zeros. When you substitute 0 back in for f of x, you get -4 for y. And substituting 1 in, you get -2 for y. So notice, sorry, I'm still getting used to this tablet. Notice that from the -1, 0, our graph went down to -4, and then it started to come back up. So actually this one right here is our turning point. So plotting all of these pieces of information, and I just realized I forgot to write these as ordered pairs for you, so I'm going to do that quickly. 0 for y. We get 4/3, 0, so I'm going to try and plot. I'm going to count each of these as 1 since my values here are all within 5. So here's 1 1/3, it'll be a little bit more. Here we've got -1, 0. And then our turning point was at 0, -4. So I'm going to go down here. And I'm going to make sure that my graph matches the shape that I got here. It should look a bit like a W. So we're going to come down through here, and back up through here. So in this case, because I knew it opened up at both ends and I only had one turning point, it ended up looking more like a parabola than a W. And the reason that happened is that these zeros were imaginary. If these had been real zeros, we would have gotten a couple more turning points and we would have had the shape of our graph looking more like a W.